Welcome back from the break, everyone. Our next talk is about infinity algebras, BB formalism, and discrete approximations to the continuum. And I'm happy to introduce Ruth Lawrence from the Hebrew University of Jerusalem. Ruth.
Thank you. Well, I want to thank the organizers for inviting me. It's a great pleasure to be here. I'm afraid the BB formalism part isn't really into it. But apart from that. Okay, so, yes, so this is part of a long-term project, and I'm just talking about some little part of it in which I've been involved. Long-term project of Dennis's. Okay, so what's the main theme? To find a way of discretizing PDEs, such as Navier-Stokes, in such a way that the system produced will have solutions that reflect better than we have currently the structure of the solutions of the original equation. So that's the goal of many people. So in the continuum model, for example, here we have U is a vector-valued function of space and time, and we have derivatives with respect to space and time. And the discretization, they say it should preserve important features of a solution. The natural form would produce, instead of a function, a vector-valued function of a continuum and time, at least if we discretize in spatial directions, you would expect a function on lattice points. You still have the ordinary derivative with respect to time, and in the spatial direction, the standard discretization would replace the derivative by a divided difference. Maybe one-sided, maybe symmetric. But the problem we find immediately is that the equations of motion, so for example here, the Navier-Stokes equation has different forms which are equivalent in the continuum formulation, the convective form here, conservative form there. But when you discretize in the simple-minded way, you produce equations which have limits formally which are equivalent, but which have very different behavior. The solutions have very different behavior in the discretized form. So we have to find some other way of picking what would be an appropriate discretization. Okay, now why are these equivalent in the continuous form? Well, it usually comes down to some sort of Leibniz derivative of a product. So in this case, for example, here, the terms here are both sort of divergent, and one of these terms vanishes, the divergence vanishes. Okay, so the problem when you discretize in this simple sense is Leibniz not holding. In other words, that you had something of this sort in the continuum, one-dimensional setting, which when you discretize, so here I've discretized using the dividing difference on one side, this would be your dividing difference for f times g, and it does not hold that this is equality. Okay, so true that it doesn't hold. On the other hand, if you tweak the right-hand side very slightly, it will hold. So, for example, if you change just one of these coefficients from g of x or f of x, you shift one of them, either one, then it will be an equality. If you don't want to do that, you can leave these both the same, then of course it's not an equality, so there's some difference term, and this is the difference term. Okay, so if you're using a one-sided divided difference, then correct forms of Leibniz in this case, in this one-dimensional case, would be any of these three. So here we have a translation, and here we have the error term, which as you see is already h times something, h times the product of divided differences. Of course, these aren't symmetric, but you have to give up something. Okay, now, so let's look at this a little more intelligently, use these ideas of algebraic topology. So instead of just thinking of the equation in terms of a function of space and time, let's think of it in terms of a time-dependent differential form. So then you hold the derivative in the time direction, but as in the spatial direction, we now think of the operators that we have. We have the D, we have stereo product, and we have star operators. So then you can take the equations and write them just in terms of that. And for the algebraic side of the picture, in the spatial direction now, we have the set of differential forms forming a differential graded algebra. In other words, we have graded commutative, associative, and Leibniz. So the idea is, the part that I'm going to talk about in this lecture is just, from the algebraic point of view, what sort of structures can you generate, algebraic structures can you generate, which may be good in certain senses, the point being that you cannot, in a discrete setting, have all three. So you have to drop something. So there's no finite dimensional model on cells which preserves homology and such that is commutative, associative, and Leibniz. So we have to drop one of these properties, but the idea is to drop it in such a way that then you can correct it. You can either correct it by going to some sort of infinity structure, or you can at least know what the errors are quantitatively in such a way you can do something with it. Okay, so you start by subdividing into cells. Instead of having a continuum, you have chains and cochains, and in place of the D, you have either a boundary, degree -1, or a co-boundary, fundamental point being the square had better be always 0. That is not something that we ever drop, otherwise we don't really have anything. Okay, so the aim is to discuss different algebraic structures which may provide what one might call a quantization of spatial algebra, which will be suitable enough for what we need. And each one starts with a finite model which lacks one of these properties, and then tries to complete it using some algebraic procedure of adding corrections. So, as I said before, the resulting object you can either think of as some type of affinity algebra, either named as such or otherwise. And another way of looking at that is as a sequence of finite dimensional models with these quantitative estimates for the error terms. Okay, so this is Dennis's lattice model of hydrodynamics. So he has two models. In fact, the point being that they were on a lattice which has this bicolored structure, so that if the lattice has lattice parameter h, then the chains or cochains that you consider will be all cubes of different dimensions, but with edge length 2h. And the nice point about that is that when you have edge length 2h, then every cell will have a center which will be in the lattice. And that makes it much easier to define both wedge and star in a nice symmetric way. Oops. Okay. So these are the equations that Dennis wrote down, but we're not dealing with the time variation, so we really don't deal with the algebra. But the point is, you can see here, so this is the momentum discretization in terms of this VL, which is a vector-valued zero chain, which also in terms of this bracket thing here, you can consider as equivalent to a scalar-valued one chain. And then the operators, you can see, well, there are other objects here, but they're related, and the operators are the star, the delta, some sort of multiplication, and of course, the Laplacian you can get from d star plus d star d in the usual way, and similarly, the condition on divergence free is written in terms of the same operators. Okay, so, and then there is another model, which came, what he calls the vorticity model, discretization, which, again, in the limit, or continuum limit, is one of the two standard forms of the Stokes equation, and so equivalent, but in this form, so here n, there, in the first form, we had a vector-valued zero chain, and now n is a cochain. And you can derive from this system both that the vorticity behaves like in the continuum, it flows represents like the flow, and that energy is preserved. And it's that energy conservation which you can't show in the first formulation, which seems to be the reason why when Dennis' collaborators did numerical simulations, they found that those two models behaved extremely differently. Okay, so let's go back to the algebraic side, looking at the models on this lattice. So ignore again the time story and just look at the structure that we have. Okay, so we have a bicolored lattice, and whether we look at chains or at cochains, one can consider them as divided up by where their center is. So in other words, the complex we have is a sum over the lattice, though that part which is at any, whose center is at any point, will be given as the exterior algebra of the tangent space there, R3, since we're just dealing in 3 dimensions. And our lattice will be a periodic lattice of even size in all the directions. Okay, so chains, combinatorial chains are given by their type, which means, so this is the type with what dimension it is and which direction it points, and its center, which will be some point in the lattice. So this is what we have. And we have this typical 1, 3, 3, 1 structure from the exterior algebra. And now we can put the operations on. So a general element of C, a general chain, will be a linear combination of these.
So can you go back? What was this 1, 3, 3, 1?
Oh, just from the dimensions. I mean, if you have a point, it's a point. If you have an edge, you have 3 different directions. You have face, you have 3 different coordinate planes, and the cube is a cube. So that was all. But that comes, I mean, the 1, 3, 3, 1, that structure is binomial coefficients because they come from the exterior algebra of R3, which was the tangent space. I mean, we're just dealing with R3, but we could deal with a more general manifold or a different dimension. So I'm saying everything just in R3, but it applies. Sorry, that was more generally. Yes, those are the pictures themselves. So a general element of the chain complex is a linear combination of these basis elements. And so it can be given, so formally speaking, what is the data we have here? So these were the basis elements, namely a type, with 1 of 8 possible types. I put all the dimensions together, and the center. And then, of course, you have coefficients. So these are, we have 8 functions here, depending on the type, 8 functions of lattice points, the same lattice region. Okay. Now, what are the operations? Well, we have what we expect. We have a boundary. It's just ordinary geometric boundary. And the square, of course, will be 0. And we have multiplication. So here we're going to define multiplication to be pointwise. So we're going to use the structure at the point that it was an exterior bound and just define it pointwise. And, well, we can use that, but then we can also define star, but we didn't write that here. Exactly the same with cochains. Again, combinatorially, because the cubic lattice is self-dual, we have exactly the same data here. But in order to distinguish it, I use the notation of di that we use for differential forms to recall that we're dealing with cochains. We have 8 functions again, 8 lattice functions. And now the operations, well, we have co-boundary. Well, of course, the boundary went down in dimension, the co-boundary goes up in dimension, the square is 0 again, you have star as usual. And now the wedge will be like the wedge is usually for differential forms. So, as I said, the linear structure of these 2 algebras is identical, but the interaction of the D and the multiplication is very different in these 2 cases, as we will see. Okay, so the main point is that the wedge, as we've defined it, will be commutative, gradient commutative, and associative, but what we've lost is Leibniz, and we're just saying that we're happy to do that and see what structure we have. So,
Could you say what star does?
No, I didn't say what star does, but it's very simple. So on the basis element, it just takes IA to I complement A. So you just change the type to the complementary type with a sign at the same.
It's pointwise.
Pointwise, yes. Everything is pointwise. Makes life very easy. So you naturally have the graded commutative associativity. Yes. Okay, but of course you can't have everything. In other words, we won't have Leibniz. So let's just look in the one-dimensional case. There we would have like a circle to some even number of lattice points, and we only have, so in cochains we only have 0 and 1-dimensional. So the 0 cochain is a function, and the 1 cochain is, well, it's also the same data that we'll just write dx. So a general cochain is as such, and the co-boundary will push up, so we will just have the f part will go to 1 cochain, and the g part will go to 0. And the multiplication will be what you would expect, just that. And on the other side, if you look at chains, well, similarly, so a 0 chain is points, and the 1 chain are little intervals, so again, it's like this, there are 2 H intervals, center is at A, general chain is here, multiplication is as you would expect, and the boundary, well, the boundary of a point is empty, and the boundary of an interval is a difference which you could rank. So this is what we have. And in the continuum limit, so if you scale by to h, then indeed you will get to the, this is just a difference. As you would expect, the continuum limit will be the boundary and co-boundary operator as you expect. Okay, so what about the error from Leibniz? So this is slightly different calculation from the one I had before because everything is symmetric difference instead. So there's no formula which works when you don't change these. There's no way of just shifting one of them and getting a correct formula. And given that we're going to act pointwise, we don't want to shift either of them. So here, the pointwise product is just literally multiply f by g pointwise. And this is the error term. So the error term you can't write in terms of the symmetrized differences, but you can write it as a sum of products of one-sided differences, but the important part being times h over 2. So in other words, the error is of order h. Okay, so that's what happens in one dimension. More generally, you can do something also. So what's about the general theory of these algebras? So this is really work of Dennis and some of this was in Randa's thesis, I don't know. Maybe it was, some of it was from before that, perhaps. Okay, so we have a graded vector space with commutative associative multiplication and a square 0 differential, which is graded plus or minus 1, but does not satisfy Leibniz. So how do we analyze the structure of the errors that appear? Well, you look at what's called higher infinitesimal cumulants. So D1 is just D, just the original D. D2 will be the error from D satisfying Leibniz, so by the difference from these two sides of the equation, which is dependent on A and B. So you have, okay, so this is D2, which you can also think of as the commutator of D and multiplication. So that's the first cumulant, which is the error from Leibniz. Then the D3 will be a sum of 7 terms. So you notice that here, what we have is the structure here. We have D of the product and then minus 3 terms where we're taking D of a pair times the third one with appropriate signs, which are the cosmic signs, and then plus the 3 Ds of a single element times the product, and then we have no unit, so we don't have the 8th term, so there are 7 terms, so it's 2 to the n minus 1 times. Structure. And this is the second cumulant. This second cumulant, well, so when this is is 0, when the first cumulant is 0, then Leibniz is satisfied. When the second cumulant is 0, we have a 7-term relation. And that's precisely saying that you have a BV algebra. So the second cumulant you can think of as the error from BV. And because D2 is 0, then so will D3, because you can write D3 as a combination of D2. And similarly, that will hold at any level. So if you ever had perfect agreement to some level, then that would be a finite error term. Okay, and then you carry on. So the high infinitesimal cumulants are precisely this series of maps. They can be thought of as maps from the symmetric algebra of A to A. The first one being D, the second one being the bracket of D with M, and the others being something else. Okay. Now, if you want to understand this nicely, I'm not going to go into all of this, but then you should think of S star A as having a coalgebra structure, an actual coalgebra structure. And that allows you to define notions of a coalgebra map and a coderivation as maps from S star A to S star A. And it also allows you to take any map from S star A to A and to extend it uniquely either to a coalgebra map or to a coderivation. So I didn't write the coalgebra map, but for a coderivation we shall write it as we have. So in particular, the higher infinitesimal cumulants that we just defined, they are maps here from S star A to A, they're various brackets. And they can be extended to coderivations. The point of that is that you now have all the maps in the same spot, and you can add them up. So these are the D's, we just talked about, the high infinitesimal cumulants, and you can extend them to coderivations. And this is what they look like when you do that. Okay, so now they're all maps from S star A to S star A. The original D, well, it just acts on one term at a time. So it's preserving the order of the S star. Here it's 0 unless you've got two elements to act on, and then it will act on pairs, so the wedge is going down by 1. Here again it starts only at 3, and so on. Okay, so you have some complicated system, and you can add them up. And now you get a big map. And the magic thing is that this is a square 0 map, which is graded, plus or minus 1 graded, and its first two terms are, one came from D, and the other came from the bracket of D and M. So, well, why is this important? Because this is the typical way that you make an infinity structure. You start with something which had square 0. And then you have something else, which is a chain map, meaning it commutes with the first one. But now, well, now this doesn't have square 0. So if this had square 0, and they commuted, and that had square 0, then the sum would have square 0. But it doesn't. So then, if you want to have the combination having square 0, you're going to have to add more terms. So you can ask this problem the other way around if you didn't know the answer. If you just had this and that, and you didn't have the higher cumulants, you could ask, what terms would you have to add to somehow correct for the fact that the square wasn't 0, and you can keep doing that iteratively. Okay, so in this case, life is rather easy because we're handed with the answer to the question. So this was D squared was 0 at the beginning, and so this first term was, and similarly the next one, because, so these are all operators. So when you could, the Jacobi identity of course holds for operators, and so we can write this, and then since these are operators of grading minus 1, the bracket just means twice the square, so it's a square plus 0, then of course it will be 0. Okay, so let's say D2 squared is not 0, and therefore we have to add corrections. And what corrections do we have to add? Well, we just said the answer. We didn't prove it, but we just gave the answer. And why is that so? Well, the reason is that actually this new D that we've created is nothing other than the conjugate of the original object that had square 0. So of course it has square 0. But this is all rather trivializing it, but it's very beautiful all the same. Where this map tau is some map called the cumulant bijection, also from S star A to itself, and it has inside it somehow packed up in a very compact way the multiplication. So this tau depends on nothing but the multiplication. When you do this conjugation, you conjugate something with square 0 to something with square 0. This, except that now what you have is really a sum, an infinite number of terms that all behave differently. The Taylor coefficients of that peel off all these higher cumulants, infinitesimal cumulants. Okay, so that's a general theory. So whenever you have a commutative, very commutative, associative structure with a differential which has square 0 but does not satisfy Leibniz, you can go and do all that and produce your big D. Or you can, if you don't want to think of it in terms of big D, you can just think of it as these infinitesimal cumulants, these DKs, which are symmetric brackets dependent on a K-tuple of whatever it was we had in the algebra. Okay, so now we go back to the particular model we were talking about, and we have two sides here. We can either deal with cochains and the co-boundary with the wedge, or we can do the same with chains and the boundary. And we get rather different results. So when we're using cochains, we find that this bracket, the K-tuple of cochains, is divisible by h to the k minus 1. What does that mean? It means you can pull a factor h to the k minus 1 out, and then you will have here a sum of products of divided differences of the functions that appear in the cochains. Okay. Now, if you do the same with chains, well, you get this power is k minus 2. What does that mean? So let's think about it again. So as h goes to 0, both of these were supposed to be approximating the continuum. But in this case, d1, it was just undivided difference, and that goes to the usual derivative. And d2, well, if you see k is 2 here, you have a factor of h, so d2 goes to 0. What was d2? d2 was the error from Leibniz. So Leibniz is satisfied in the limit, which means that the structure approaches the differential graded algebra. What was it? A differential formula. That's what we knew at the start. That's why we began all this. Okay. If we do the same with chains, on the other hand, then when k is 2, well, you can't pull out a factor of h. So in fact, it doesn't go to 0, and indeed it shouldn't have gone to 0, because what it goes to is this pair, this commutator, which is the Lie bracket of vector fields, or more generally, the Schaden-Nauhaus bracket of polyvector fields. On the other hand, d3 does go to 0, so that means that we have a 7-term relation, we have a BB algebra. So the structure approaches the BB algebra of polyvector fields. The polyvector fields are just, basically, we've just got this S star of basic vector fields. Okay, so that is the structure, but not only can one say this in a vague way, we actually have expressions for what these sums of products are, well, the visibility power, of course, we have. Okay, and in addition, everything is supposed to be functorial, which means that if you subdivide, then, well, you have, this is actually general statement, it doesn't depend on the particular fact that this was geometric, but that's drawn in the geometric case. So if you have some sort of a subdivision map, then you have natural maps on the chains and cochains. In one direction you're crumbling, the other direction you're integrating, you're summing. These maps, what do they mean? They're natural. They commute with the boundary, intertwine with the boundary map. But not with multiplication, because the average of the product is not the product of the averages. So, what do you get? Well, okay, so here this is a cube which is supposed to tell you something. So here, on the left-hand side, we have the S star of the algebra, say, in this picture. On the right-hand side, they're all S star of the algebra in the finer grained picture. Now, we have, between these two, we have pick one of the directions, we have, say, a crumbling map. And that will give you, then, at this level, the natural corresponding map between the S stars of the same spaces. Okay. Now, this commuted with the D, and therefore we have a commuting square sitting up here. Okay, now moving down to the lower layer, this yes?
Can you say what the crumbling map is?
Oh, so that just takes a chain and writes it as a sum, literally, of the pieces of which it was made. So you had a square, sum of 4 pieces there. Okay? Nothing clever. And in the opposite direction, it would just be taking the average of the values. Don't take function to function. Okay, so this tau, well, these were the cumulant bijections. And if you remember, there was this statement that the big D was the conjugate of the original D by the tau. So now we have commuting squares on these two sides. What we want to do is understand how to relate the D and the D bar. Well, if we can find a sigma here, which will close it, well, of course you can. You just go around this picture. This may not be invertible, but the tau is, so you just go up here, around there, down there. That will give you a map which will intertwine D to D bar. And what is this map? Well, it is just the commutative cumulants of the crumbling map. In this case. So those commutative cumulants are precisely the objects that make up the sigma, which will intertwine between the D and the D bar. Okay, so in a particular case, like the case that we have here, you have a very precise crumbling map you can write down, and then you can compute the commutative cumulants and see what is their structure. And you'll find that indeed they have this right divisibility properties, so they preserve the properties you had here. So each of these statements turns into an infinite family of equations relating the two maps on the two sides. Okay, so
can I
yes?
ask you a question? Can you go
Sure.
back?
Certainly.
So I think there's some point I'm not understanding very well, because the tau is an isomorphism.
Yes.
So you're transporting something with just a differential,
Yes.
kind of isomorphically on this
Well,
symmetrical
yes,
algebra.
so really we have to go back somewhat further, I think. We have to go back to the original, to this thing. Okay? So this, indeed, well, maybe the next, yes, here. Okay, so this we know had square 0, because that's where we started.
Right.
We conjugated by tau, which is somehow packaging up the multiplication, which doesn't behave nicely with respect to D.
Great.
And when you do this, you get this big D,
Right.
which now has an infinite number of components. The first one is D. The second one is the error from Leibniz. And the rest are corrections which make the square 0. Well, of course the square is 0 because that's what it was.
Right.
But if you didn't know that, you've got this magic object here which has square 0, which has all these corrections.
Right.
And that's telling you at all the levels, well, what was the error from Leibniz? Yes, because they had these are the infinitesimal higher cumulants. So what we've just found just now is that if we do this on the two sides of the picture, where this is not an isomorphism, you have a crumbling map or an integration map, then the two Ds are related to each other by intertwining by something which is again cumulants, but not infinitesimal cumulants this time. It's the cumulants of the multiplication of the crumbling map with respect to the two multiplications on the two sides. So, for example, the first level would be this AB bar minus A bar B bar. So that's the first. The next one would be sums of terms like that, just like the infinitesimal ones that we had before. Okay, so the content of this is just computing those infinitesimal cumulants or commutative cumulants for the particular case of the lattice and its operators, and finding that they have these divisibility properties. Okay, so all that was about the case of commutative, associative, and no Leibniz.
What did the little red arrows mean in the last slide, at the bottom right?
Sorry?
What are those
Here.
little squiggly red arrows mean?
These ones?
No, the bottom right.
Oh, these?
Yeah.
I think it just means that yes, it just means there are two cases. As before, there were two cases. So in this case, I'm going to put a colon. Then the renormalization map will have this divisibility. It doesn't mean anything. I mean, say in this case, and in that case we have two cases, chains of the cochain.
Is it? I can't read the green. Is it? Are they both the same?
No, one is going from a fine cochain to a coarse cochain.
No, I meant
Oh.
the last thing. Is it?
I
Are they
can't
both
read that.
h to the k minus 1 and h to the k minus 2 like last time, or?
No, they're both h to the k minus 1.
They're both.
But when you write the equations down, so you have a system, I mean, you've got a sum times something, it's another sum times a sum. So if you look at the coefficients, then you'll have a system, triangular system of equations on both sides, and you'll find they have the right orders. So, yes, it's correct that they didn't change in this case, but they do conjugate correctly. Okay, so this was no Leibniz, so now we want to talk about different, so these two don't fit together in some sense, but they are different ways of looking at the geometry of discretization. Okay, so what happens if you want, sorry, this is Leibniz. Okay, so let's just look at the one-dimensional situation. So, of course, zero cochains are functions on vertices, one cochains are functions on edges. And what would multiplication have to be? So we're just sort of trying to look at the general picture, what can we do? So, well, there's no trouble with zero cochains because they're functions on vertices. You can multiply functions on vertices, just multiply them, and they're localized, so there's nothing to do. Whatever you do, this would be how you define. Now, how would you define a zero cochain multiplied by one cochain? You should be getting a one cochain, whatever this thing is. How would you define it? Well, you have to specify what its valuation is on an edge. So let's take an edge. What could it be? Well, it's supposed to be something from F times something from G. G was a one cochain, so G has an evaluation on E. But F was a zero cochain, so you need to know it's a point. So either you have such a thing as a point in the middle, like we were talking about before, or if you don't have a point in the middle, you're going to have to pick either A or B. Okay, so that's really all the choices you have. And of course, if you had it in the other direction, you'd have the other direction. So if you put all the cochains together, then you might want to take sums of pieces of these two. Okay, so what this is really related to cellular approximation to the diagonal. If you want to multiply these, you can just multiply cochains, and you get a cochain on x cross x, and then if you have a diagonal, then you can restrict it to the diagonal, a cellular approximation to the diagonal. So, for example, in this case, we're doing one dimension, it's just an edge. So this is x cross x, so you can either take the sum of these two, or you can take the sum of these two. And that would give you two different products. So if you took the one going up here, that means we're talking about this product. Okay. But if you use that product, then it's obviously not commutative, because we've got an A here and a B there. It is associative, and it does satisfy Leibniz, and it is just the Alexander-Whitney cut product. Or you could do it the other way around, which is just the opposite multiplication, and then it's just as bad or good. In other words, they're both non-commutative, associative, and Leibniz. Now, if you take the average, then, well, the average will be commutative by definition. The condition for being Leibniz is a linear condition on the multiplication. It's that multiplication commutes with D, and so it's still Leibniz.
So, sorry, in that second line, is that written right?
No.
Okay.
Sorry. It should have been f of b times g of e plus f of e
B in
times
the
g of
first
a.
and A in the
Yes, sorry. But the average seems to be right. So you can guess what it must have been.
Okay.
Yes. So it will be commutative by definition. It will be Leibniz because the condition was linear. But the associativity condition is not linear. It's a composition of two multiplications. So it no longer holds. Okay, so we're now back in the same situation of having to lose something. Every time we fix one thing, we lose something else, unless we're prepared to go to infinity. So what we were just talking about just now are these two. You see, you can, I still haven't got it right. You can either have it associative with Leibniz but not commutative, or you can take the average and you will have commutative Leibniz but not associative, or in the case when the edges were of length 2h, then you can do it pointwise, and you can use the middle. And then it will be commutative and associative, but now you've lost Leibniz. Okay? So this is what we were talking about the first half. And now, well, this was the Alexander-Whitney cut product, so I won't say any more about that, but now I'll talk about this story. So we're going to call these m prime and m double prime, well, somehow, at some point, I'd like to talk about them like that, so we'll just do them like that. And you can do this in higher dimensions too. We're just playing with a toy model of one-dimensional model just to make it easy to be able to draw things. You can do multiplication pointwise, etc. It's exactly what we've been doing. Now you can do the general Alexander-Whitney cut product. You can take its opposite, you can take its average, and the average will be, again, we have to say, it will be commutative and Leibniz, but not associative. But, equivalently, this average, now if we think about it on chains, we shift the grading, then, well, you can, what we were doing up here was on cochains. So if you take, instead of having a product on cochains, we'll have a co-product on chains. It was commutative or graded commutative, so it will be graded co-commutative. So it will be a map to the Lie bracket of C and C. Okay, and it satisfies Leibniz, so this will be a differential graded Lie algebra. So we now have a differential graded Lie algebra on chains. At least that's the idea, that's what we want.
You mean a Coley algebra?
Yes.
Okay.
Well, okay, so no, I didn't mean that. No, because I did. What I meant is, sorry, we don't have a differential graded Lie algebra yet. We just have a map from C to the bracket of C and C, which you can think of as a Lie bracket because of the commutativity. Okay. So the next slide. I mean, that's where we're heading, but actually what we have. So okay, so this is again due to Dennis. For any cell complex, you can make a free differential graded Lie algebra, one generator for each cell. The grading will be the geometric dimension minus 1. The part of the differential which doesn't change the number of brackets will be just the geometric boundary. So for example, if you just act on the generator, then it will give you the geometric boundary. And on points, 0 cells, the differential is supposed to look like this. So this is Laurent-Cartan equation. So Dennis showed that such a D always exists. D squared is 0, of course. It's not unique, but you can always construct a local one, which, and the proof is iterative, cell by cell, dimension by dimension. In order to start the process, you need a D1, which is the geometric boundary with square 0, and you need a chain map. So in this case, the chain map I'm going to use is this M double prime. Okay, so that's how it connects with the previous slide. So you can start with this, and then you can use Dennis's procedure, and it will produce something. Well, except there are some choices that have to be made, so it's not unique, but it will produce a DGLA. It seems to be unique up to DGLA isomorphism. Right?
And what does local mean?
Oh, in the silent cell. So D of any cell, a generator, yes, will involve only cells in the closure of that cell. And because of that, you can solve it dimension by dimension, going up and cell by cell. Okay, so the simplest example is the interval, and that was the first paper we wrote together. So there is this formula, which I wrote down also, and well, it involves Bernoulli numbers, which is mysterious where this would come from. Okay, and then what is this? So this is, if you take an interval, you have 2 points and an edge. So the corresponding free differential graded Lie algebra will have 3 generators. It will be a free yes, on 3 generators. A and B will have grading minus 1, so that's already a bit weird. And E will have grading 0, as you normally have in the algebra. So having grading minus 1, that means that A bracket A is not 0. Okay, but E bracket E would be 0. Okay, so, but now we need to make it into a differential graded Lie algebra, not just a graded Lie algebra, so we need to tell you what the D is on every generator. So the D on the point is prescribed, and we have no freedom of movement. So we have D of A, and we have D of B, and the only question left is what's D of E? So there is a unique expression which works. What does works mean? D squared is 0. Okay, again, it had to start with the geometric boundary. The geometric boundary of the interval is b minus a. So we've been told this, and it's a unique way of continuing in such a way that this square will be 0. Let me tell you that even if you knew this formula, with these Bernoulli coefficients, proving that if you know nothing else, didn't use any geometric insight, proving that this particular formula gives you d squared is 0 is highly non-trivial, and gave some new identities on Bernoulli numbers. So it's strange. Okay. Now, on the other hand, this is unique.
Hey, could you just say a word or two about why the Bernoulli number?
Yes, so this is what's coming.
Oh.
Okay, so rather than writing down a formula, you can just say one word, one line, well, I can give you 2 lines. So first of all, if you have any element of A0, so that's anything like an edge like object, but it doesn't have to be actually geometrically come from an edge, the gradient has to be 0, generates a flow on the whole of A. So A is this algebra, it was C on the previous page, but I'm calling it A because now we have the right grading, we've shifted the gradient. This is the algebra, okay. The DGLA. And so the flow is generated by this. So it's U is the thing that's flowing. It's an element of A star. It depends on time. Derivative is given by this. So this looks just like a gauge transformation, and that's what it's supposed to look like. So in the case, this is natural in the case when U is a grading minus 1, in other words, it's a point. So the point is actually going to be moving, and it moves according to this. E would then be grading 0. U is grading minus 1, so this is minus 1 grading. And D of E is also grading minus 1, so everything is fine. In the case when we're not dealing with grading minus 1, then this term you ignore because it's in the wrong grading, and then you've just got a linear equation, homogeneous. It's just the action of add E, so it'll be exponential of add E. Okay, very simple. Okay, I mentioned that because you'll see why in a moment. So now, this strange formula with Bernoulli numbers reduces to the following sentence. That the condition is that the flow generated by the edge E takes A to be in unit time. So you just solve that backwards and you find this formula. And that is how you prove in an intelligent way that d squared is 0 and that everything actually works. Okay. And it's important that this flow also preserves the property we call flatness, or in other words, the vanishing of what, if you were talking about differential geometry, would be the curvature. So you remember that A and B satisfy the Maor-Cartan equation, so that means that they are flat. This vanishes. Okay. And indeed, any flow that starts at a flat element will continue along points which continue to be flat. Okay, it is still, this analogy is still intriguing. It's not entirely understood to the end, although everything that one needs has been transferred into this world. Okay, and again, everything's functorial. We said this was unique, and therefore there must be a natural map, a DGLA map between what happens when you take an interval and you subdivide it into 2 intervals. Well, of course, here A had to go to A0, B had to go to A2, and E has to map to something, well, these elements will have grading minus 1, these are the only things of grading 0, so it'll have to be some expression, the algebra expression involving E1 and E2. What is it? Well, it's Baker-Campbell-Hausdorff. What else could it be? Why is that? Well, we just said why, because if you think about this flow, then this flow is e to the power add E, and this will be e to the add E1 and add E2, so of course it would have to be Baker-Campbell-Hausdorff. Okay. But the statement we gave a moment ago as to why that might be was assuming that there were other gradings other than 0 and minus 1, which there aren't in this case. So,
excuse me.
yes.
I see, if I compare the formulas, I have a half and then I have a 12. And then up
It's
there I
also
have
a 12, because it's the other way around.
Wait.
Yes?
Up there I have a 720. Is the next term going to involve a 720?
I don't know. Okay. I don't remember what the next term is. I think it's smaller than that. I mean, and larger than that. Yes, it's not a, yes. So there are many nice formulae for Baker-Campbell-Hausdorff and then, yes, non-unique and so forth. But I won't go into that. Yes?
Also, you told us the DGLA for the left-hand side.
Yes.
The DGLA for the
Oh, it's
right-hand
local,
side.
so there's no choice. On each interval, it has to be what I've already written down. There's nothing left to talk about, so that's it.
Because it's local.
Yes, because DE1 has to be contained in the 3D algebra generated by the cells in the boundary, in the closure, which are A0, E1, and A1. And I've already written the formula, so.
You define it on the boundary.
Yes, exactly. Okay, so that's the interval. Now you can close the ends and you have a loop. And you notice that if you close the ends set B equal to A, all this disappears, so you just have a very nice simple formula. So this is what you get for a loop. I don't know why we're doing that, because then you can try and go to a disk. So you put now we've got the element G, so we've got 3 generators again, grading -1, 0, 1, up. Now we've already got trouble in the sense that we can take the bracket of A and G, and it will have grading 0, and so it will behave like an edge, but there's no geometric edge as AG, but you can flow according to it, or a combination, you know, E plus AG, you can flow according to that. Okay, well anyway, A is the only point here, so that was forced upon us. E we already know about from the previous slide, and now you have to work out what to do here, and this is the unique thing to do. So this is what you get for a disk. But now you could add an extra point on the boundary. So now, for these edges, we know what to do. We wrote them down before. Well, this is formula with the binary numbers, but written in some sort of formal notation. E means add E, and this is a formal power series. A and B we know about because they're defined. Now what about G? Well, we just said that you replace the edge by the BCH, the Baker-Campbell-Hausdorff, so that's what you do, and you get this. So this is a model, but it's not symmetric. This is symmetric, but this isn't symmetric. Why A and not B? Okay, so there are 2 models. Well, there are an infinite number of models, but there are 2 models, but neither of those are symmetric. So this was one of my students to produce a symmetric version. So what you do, the models in some sense can be thought of as localized at a point. So the model I wrote down before was localized at A. You could write down a model localized at B. And the idea is to somehow find a point in the middle. What's a point? A point is a thing that satisfies Maor calc. So anything which is such that dx plus a half x bracket x is 0, we call a point. And we just said that that nice flowing equation, if you start at a literal point, and you flow by anything that is in, for example, half e plus f or something, then you will get to other, your solution will always be a point in that sense. Okay. Imaginary point, yes, exactly. So this is what we did. So it's actually, you don't need G in order to be able to construct these things. So you can construct a point. This is the formula for it. This is the flowing map that we had before. And you can find out how that will affect this Q here, which was the BCH. And this will then be a symmetric model. That's completely explicit. Okay, if you get a more complicated cases, so a triangle, for example. So we have a whole series of papers with students constructing rather nice explicit models. So here you need some sort of iteration to try and find the central point again. How do you find central points? Well, you can find midpoints, and you take midpoints and midpoints, it's going to work. But in order for that construction to work, you somehow need that the whole thing is flat, which means if you go around the outside, that is a loop that's supposed to be contractible, you'd like to get the identity, but there's no reason why BCH of EFG will be the identity. But there is a way of producing some other elements that I've written down here, which is such that their BCH will be the identity, and such that what I've drawn is valid. In other words, if you take E0 and flow from B for unit time, you will get to C. It's surprising that you've got this strange curved geometry. So now here, somehow, this is flat. The original thing wasn't, and this thing is. And then on that flat thing, you can do this procedure, and you can get an iterative construction with symmetric model. And then you can do it in 3 dimensions. Ah, yes. So this is some rather nice statement that those flows, whenever you have 2 points and some number, just abstractly, some number of ways of getting from one to the other by n different flows, there is an average. If you literally took the third g plus k plus h, well, it wouldn't flow from A to B in unit time. It would go who knows where. But there is some formula that lives inside the free Lie algebra on the generators, which will universally be such that it will also take A to B. And the first term gets 12 again. Yes, but it's 12 at n squared, so depending on how the average of what, so it will be here 12 and 1 over, sorry, for n is 2, you'll have a half, 1 over 48. And then goes up a little bit more terms. This is only the first 2 terms. So there'll be more with they'll only have even numbers of brackets, and there'll be further terms. Okay, and that we used in order to construct symmetric models of 3 cells. So here we did what we call a banana. Again, you have to find the center. So you take the average of these e's according to what we just wrote down and go only halfway along, and that will be a central point. Then you have to actually have a model that's not symmetric, say based at the endpoint for a 3 cell, and then you move it and you get a symmetric model of the banana. And
So
then the banana,
N is related to the dimension of the cell?
no, n is related to the number of, here, if
Oh,
you have a
yeah.
banana, you have a banana with certain, yeah, the number, n is 3 for a banana, I guess. Yes. So, on the other hand, if you take this cube, I want to think of that as a 6-cell banana, because the number of maximal chains from, yes, maximal paths from A to B will be 6. So you can use that, you can use this model in the case where n is 6, and then apply the right maps to produce a model. And here it's rather nice, you can see this is the first few terms for the boundary of this 3-cell, which is a cube. Yeah? So you can see we have the sums which you expect, that's the geometric, this is the geometric boundary, just the sum of the faces. And then you have this piece here. These are, so each capital E is just add E. So these are brackets, Lie brackets of, in this case, faces and edges. What is that? That's n double prime. That's actually n double prime here. So you've got each face and opposite edge. Okay, so now, we were just saying you can't have all 3 at the same time, commutative, associative, and Leibniz. So I'm going to end by telling you that you can actually, if you're prepared to give up something else, you can actually have commutative, associative, and Leibniz. So this is, I guess, something that Dennis was working on with graduate students here, and then we started looking at it with Dennis too. So there does exist something which, well, this is on chains. You can have C0, C1, and C2. C0 are points in the H lattice. C1 hash, so these are somehow enhanced. They're sticks parallel to one of the axes, so we have 3 different axes. But I'm not just going to restrict it to sticks of length 2h. I'm going to allow sticks of length h and sticks of length 0. But I don't want to call them points. I want to call them directed objects with directions x, y, and z. And C2 will be the normal 2h squares, parallel to, so say, one of the coordinate planes. Okay, but we don't have C3. So we just have that. Grading is by codimension, so in other words, C0 is graded 2. The boundary, well, the boundary is usual. So here, there's sticks. The boundary of a stick is the difference of points in the usual way. The boundary of a plaquette is the
Grading of C0 is 3.
The grading of C0 is 3, exactly. The boundary of a plaquette will be the geometric boundary, but then we have to add some infinitesimal sticks, that I'm not telling you how you do that. But still, d squared is 0, so I'm not giving that up. The product, so now there are only 2 products that will be non-trivial.
So the boundary of the infinitesimal sticks is 0?
0, yes, it's just what you thought it was.
Okay,
yes,
sorry.
exactly. No, good question. So we have 2 products to think about. So, as I said, grading is by codimension. So if you use the numbers that are written down here, which are the dimension, then Cp cross Cq will go to Cp plus Q minus 3. Okay, so if the P plus Q isn't at least 3, you'll get 0. So in other words, the only 2 cases we've got, since we've got 0, 1, and 2, will be 2 and 2 goes to 1, or 1 and 2 goes to 0. So 2 and 2, well, this is actually what you might expect it to be. You take 2 squares, if they're parallel, or they don't intersect geometrically, intersect if you take their closures, then the answer will be 0. If they do, then the answer will be, well, you take the literal intersections. In this case, it's a stick of length 2h, but if I'd shifted it over by h in this direction, it would be a stick of length h, or if I'd shifted it further over, it would be an infinitesimal stick. You can tell the direction, because there's only one direction that's normal to both normals. Yes? The direction you should have will be the direction of the stick. The length of it will be whatever it happens to be. And then there's a sign, which will be the cross product of the normal vectors, and a power of a half, which comes from boundary effects. So for example, here, if the intersection had been at the middle of both of them, then there would be no factor of a half. In this case, we have one factor of a half because somehow this intersection is at the boundary of one of the squares. If it was the boundary of both of them, then you have a quarter. Okay, so that's that product. Then you also have a product, which I'm not writing down, which is here. And again, here you have a stick and a square. They have to be transverse. They have to intersect literally geometrically. You have a point. That's the point. But the factor I'm not telling you about. So these are two of the cases, but there are two more. And then, well, it works. Meaning what? Meaning it's commutative, it's associative, and Leibniz. And t squared is 0. So what happened? Well, of course, what happened was, first of all, I omitted C3. And secondly, I put these, Dennis put these extra sticks in, infinitesimal sticks, and so the homology isn't preserved. So we've done something to it. But on the other hand, we do get something, this is connected with both the linking form and a very symmetric triple intersection form, which displays the right symmetries that we would like to have. And so I think this is really a good start. So we've only discussed these different algebraic structures, and the next stage, which I'm going to say nothing about, because the BV formalism, is to develop an evolution which we can then use to get numerical approximations, which should mimic somehow, in a global sense, the symmetries which were present in the continuum model. So by that I mean, for example, this trivalent, this free form and linking form, without boundary effects that somehow have the original symmetries. So we're working on this. We hope to have something soon. And thank you for coming.
So in this last model that you have the three identities holding,
Yes.
is there a natural co-product which is compatible with these Alexander Whitney type co-product?
That is compatible with intersection product?
With the intersection product and the
Yes.
boundary.
I don't know. The answer may be, well, there's no star, obviously. So that might be difficult. Yeah. Yeah.
So how about the uniqueness of the models? I mean, in the one-dimensional case, it was unique, and you gave these very symmetric versions. Like if I ask for a really symmetric, can I impose some sort of uniqueness on
Yes. So there are there are a series of theorems by Felix and I won't pronounce their names correctly. The four people who are Murillo again. They have various theorems which essentially mean that yes, up to DGLA isomorphism they are unique, but actually generating in an explicit way symmetric models is not so easy. So there are definitely, certainly higher dimensional cases, there are symmetric models that are non-unique too. But as I said, up to DGLA, isomorphism they're good.
Something that I wasn't understanding right in the banana case.
Yes.
So then you draw a cube.
Yes.
Were you claiming that you know how to explicitly give a D model? For
Oh yes, yes. I have an explicit model simply with this thing. Yes. So simply you take those 6 paths, okay, and you think of them. So for example, you might have this path, and the next one will be that path. Okay. Now it's true that they coincided here, but you think of that as one piece of the banana. Okay. So you have then a map from one to the other, and then the BCH of those things is is what's going to give you the 6 different parts, different EIs that are up there. Then you take the average of that and you proceed as usual. So,
And in the
yes.
next dimension?
Sorry.
In the next
Oh, the
dimension?
next dimension, we stopped thinking about that because this seemed,
Okay.
why you need explicit models to actually do something with it, we wanted it for a cubic lattice, so we stopped. But I guess that we passed over the difficult part. I mean, the difficult part is somehow first of all, was just separating points, but once you've done that, the difficult part is going from 1 to 2 dimensions, it seems to me. And after that, things almost commute. You've got enough space around it. It's all to do with paths, and you have enough space for things to commute. So you just have more and more BCHs. And you may have to play around a little bit, but basically things commute. So the algebra is not too difficult.
Great.
Yes.
So I'm asking because you mentioned this 4-author paper, and
Yes.
they only have explicit formulas up to dimension 3, and higher dimensions.
Oh, I see.
remain
Okay.
open.
I see. I
They're
hadn't.
working simplicity, but maybe cubically is the way to do it.
Yes. Well, the paper on the triangle came out 3 days apart or something. So yes, and I wasn't aware of their formula for the 3-cell, but I guess it's probably based on a similar sort of argument. So yes.
So the banana case has appeal.
Yes. And indeed, the central point is inside the algebra generated by the peel.
Any more questions?
Can you emphasize again on the very last example where you managed to have all the relations in your wish list?
Yes.
What did you give up?
Well, the homology is wrong because we've added some extra strange sticks to C1.
And no top cell.
And no top cell, of course, also. But maybe, yes. I mean, I think it may be sufficient for what we actually want to do. But if you were wanting just commutative associative Leibniz structure on all cells, then we didn't get that.
And then you could write the Navier-Stokes equation just with this information. That's what she meant in terms of what we want to do. But in terms of topology, it's not really a theorem that you can't do this. I mean, I don't know a theorem that you can't do everything, but if you put various natural attempts, just don't work. You know. I mean, have a finite dimensional commutative associative Leibniz. Then you can have an infinite dimensional one. Look at Whitney's book. Okay? We want a finite dimensional one. So if you try to take the Whitney construction and make it finite dimensional, you can't make the homology correct. At least on the interval. Take the interval and try to take the Whitney construction, or take any construction, try to make a quotient, and the quotient will have a homology. And so it's sort of a belief.
Is this example 3-dimensional?
Yes. Oh, yes.
Is there a 2-dimensional?
Version of it. Probably. But maybe we'd have to cross out C2 in that case.
I mean, for this much, it probably would be.
All right, well, thanks again.